Hello and welcome to my new video. Satellites are measuring nearly everything on this, from wind speeds over the Northern Atlantic to the use of cover crops in a certain location in Germany. Satellites will tell you. This way they are producing a global picture consisting of many local details. They are revolutionizing, almost unnoticed, our view on our planet. Today we can watch almost in real time every location on this planet. We can download local weather data or witness local catastrophes. Will this global information network also generate some kind of global consciousness? A consciousness of connectedness and togetherness? This question is too big for this video. We will only talk about how satellites nowadays are generating this wealth of data. It all started with photography. This is one of the oldest methods for satellites to do observation on this planet. In the background, there is such a photo of the North Sea taken by the Copernicus Sentinel program. Electromagnetic radiation, visible light or microwaves, is still the most important channel for satellites to get their data. These radiation types, however, are used in a much more sophisticated way than in simple photography. To understand these approaches, we have to talk about some basic properties of electromagnetic radiation in the first part of the video. Let's start with a typical satellite picture. This one has been taken by the Copernicus Sentinel program from the North Sea. How are such pictures taken? Very simple. Radiation from the sun is reflected by the Earth's surface and recorded by a camera on the satellite. The satellite is taking a picture. Before looking at more sophisticated techniques, we have to learn a bit more about the nature of light. What is light? Light is a coupled oscillation of the magnetic and electric field, which is propagating in space at very high speed, at light speed. The frequency of this radiation tells how many oscillations occur in 1 second. And the wavelength of this radiation tells which distance is covered during one oscillation. A high frequency corresponds to a small wavelength, and a low frequency corresponds to a large wavelength. Examples for radiation with high frequencies are gamma rays or X-rays, while examples for radiation with low frequencies and large wavelengths are radio waves. And what about visible light? This scale covers the whole range of electromagnetic radiation from the very short wavelengths radiation, gamma radiation, to very long wavelengths radiation, radio waves. The scale is logarithmic. 10 to the power of minus 12 refers to 1 picometer. This is smaller than the radius of one hydrogen atom, while 10 to the power of 3 refers to 1000 meters, so 1 kilometer. Light covers only a pretty small region from more or less from the center of this scale. Only radiation from this small band can be seen by the naked eye. And you can see that the different colors refer to different wavelengths. So blue light has a slightly smaller wavelength than red light. Which kind of radiation is used by satellites? Which radiation is visible for them? Besides visible light, they sometimes use also infrared light, that is radiation emitted by heated objects. But besides of these two areas, they also often use microwaves. These is radiation with a wavelength of millimeters or centimeters. Why do satellites use microwaves? What is the advantage of being able to see microwaves in the sky? Well, one point is the behavior towards clouds. Visible light is clearly reflected by light, so satellites cannot see the area below the clouds. This is not the case for microwaves. Microwaves are not reflected by clouds. They can just go through the clouds, and this means satellites which can see microwaves can observe the ground even when there are clouds in the sky. Microwaves, on the other hand, are reflected by raindrops, and therefore it is possible to use microwaves for monitoring rainfall on Earth. These were the basics of satellite measurements. Electromagnetic rays are oscillations spreading in space with frequency and wavelength as the most important properties. Depending on the wavelengths, there are different types of radiation. Gamma rays and X-rays with very short wavelength, then visible light, infrared light, and microwave with increasing longer wavelengths, and finally radio waves with very large wavelengths. Satellites primarily use visible light and microwaves for their measurements. But how are satellites actually using this radiation? Are they simply taking pictures with visible light or microwaves? It is with and without clouds? Of course not. In the remaining part of this video, I will show you which wealth of information satellites can extract from visible light or microwaves recorded. Modern satellites often are producing the radiation they will use for measurements by themselves. They are producing it in form of very short pulses, several hundreds per second, and emitting these pulses towards Earth. Now let's imagine satellites could only measure the intensity of the reflected radiation. In this case, they would only be able to produce black and white pictures. If you want to measure colors, then you have to be able to measure intensity in different wavelength areas separately, independently from each other. Then you will come to color pictures. And these color pictures contain much more information than only black and white pictures. If you look, for example, at these streaks in the North Sea, then you can clearly see that these are algal blooms on this color picture. If you look on the black and white picture, these streaks might also be cloud or some remnants of clouds. Besides intensity and color of the radiation reflected from Earth, you can also have a look at the shape of the wave packages. This shape contains information as well, information about the roughness of the surface where the radiation has been reflected from. For example, if you have a forest, then the signals will become much more fuzzy, much more irregular than when you have a field or a meadow. On the sea, this roughness of the surface corresponds to swell, and this means it corresponds to wind speeds. You all know Doppler effect from car traffic, where the Doppler effect allows to measure car velocities. When a car is approaching a camera, then the radiation used will have a somewhat shorter wavelength, and this decrease in wavelengths corresponds to the velocity of the car. We can also use this Doppler effect in the atmosphere for measuring, but not for measuring car velocities, but cloud velocities. And this will correspond then to wind velocities, of course. Finally, satellites can measure very precisely how much time a given signal needs to reach Earth's surface and come back to the satellite. And this runtime corresponds to very precise measurements of the distance between the satellite and the Earth's surface. And this means satellite this way can generate very precise elevation profiles of the surface of our planet. These profiles, for example, can be used to find ancient castles or ancient settlements. Here I'm showing you a height model of Iceland as an example. In summary, electromagnetic radiation can contain a wealth of information. Intensity and wavelength of the radiation thrown back tell many things about the respective areas. The shape of wave packages corresponds to roughness of these areas. Doppler effects allow calculating relative velocities, and runtime of signals leads to precise elevation profiles. Now that I have shortly introduced all these measurement approaches, my next video will become somewhat more practical. We will learn about a range of practical applications of these methods. See you then.